On average, half the plants of a particular variety produce red flowers and the rest produce blue flowers. And chooses 8 plants of this variety at random. Find the probability that more than 6 produce red flowers. So like we said, the first thing to notice here is we're not told whether it's binomial or geometric or what we're supposed to do with it. But there is a big clue. As soon as we're given a fixed number of trials, it must be binomial. So we can start by saying this is a binomial distribution with that being 8. Now what's the probability of a success? It's a half, isn't it? And the way I set this up is that x is the number of red plants. Plants producing red flowers, I should say. Okay, now we've been asked to find the probability that x is more than 6. Okay. Well, let's think about this. What we could do, that means x is 7 or 8, doesn't it? So you've got a couple of choices here. You could use the formula that we've just been using, the NCR, p to the r, q to the n minus r formula, and do that. So I just said the formula, but I did, yeah. We could use that and work it out for x equals 7 and x equals 8. But remember, 8 is in the formula booklet on one of those tables. So we could use the tables as well. If we're going to use the tables, we need to turn it into a less than or equal to probability. X can be 0, 1, 2, 3, 4, 5, 6, 7 or 8. We want it to be greater than 6, which is the opposite of it being less than or equal to 6. So this is 1 minus the probability that x is less than or equal to 6. So we're going to go for our tables. We're going to find the n equals 8 table. It's in the first page of tables on page 10. We're going to go along to a half on the top, halfway along, and we're going to look down for the probability of x being 6, and I am getting 0.9648 out of that, which gives me a value of 0.0352. And that's it. Okay? If you had done this working out the probability of x being 7 and the probability of x being 8, you would have got that same value to 3 significant figures. So you could have done it that way as well, with the same thing. Right, then it says, Karim chooses 22 plants of this variety at random. Find the probability that the number of these plants that produce blue flowers is equal to the number that produce red flowers. Okay, 22 plants. Well, things have changed slightly, haven't they? We're now, I should use a different letter maybe, but anyway, we've now got 22 plants, still with the probability of success being a half, and I want things to be equal. Well, that means I have to have 11 of each, doesn't it? Is there 22? So that's another way of saying what we've been asked for here, is the probability of x being 11. Look in the formula booklet, we times through 16, 18, 20, it's promising, oh, 25. We haven't got a 22 table either, so we're back to using our formula again. So this is 22C11. That's 11 successes and 11 failures. So it would look like that. And if we do that, where's it gone? We're going to get 22C11 times 0.5 to the 11, and I don't know why I'm not just doing 0.5 to the 22, but I'm not. And I get 0.168 to 3 significant figures. There we go. Right. part B, hence find the probability that the number of these plants that produce blue flowers is greater than the number that produce red flowers. Hence, what's the question asking us for here, really? What we could do is we could ignore that word hence and launch into working out what's going on with this. The question is saying that x has to be greater than 11. That's it, isn't it? Because that would be the number of red flowers is more than the number of blue ones. 22, so that means we need to work out the probability of x being 12 plus 13 is 14, 15, 16, 17, 18, 19, 20, 21, 22. We need to work out all of those individual probabilities. We could do it, especially if we've got plenty of time. We've got plenty of time, we could work out all of those. That's a lot of work, isn't it? So let's think, is there another way that we can do this? Well, actually, that key here is it being a probability of a half. That means this is completely symmetrical, isn't it? Okay? It doesn't matter whether we're talking about red or blue, the probability is the same either one, so that the whole data, the whole distribution is symmetrical. Which means that the probability of having more red than blue is the same as the probability of having more blue than red. And actually, we can bring it down to there just being three things that happen. The three things that happen are, we could have more red, we could have equal, and we could have more blue. And these two things are exactly the same. And all three of these things add up to 1. So let's call, we could call it something. Let's call this probability, we've used lots of other letters already, let's call it K. This probability is exactly the same. This probability is 0.168. We worked that out a few moments ago. That's the hence bit. What can you say about all these three things? Do we know anything about what happens with all these three things together? They add up to 1, don't they? Yeah. All these three things add up to 1. So K plus 0.168 plus K equals 1, giving us 2K is 1 minus 0.168. Which is 0.832. So the probability of after is that divided by 2, which is I could have done that without the calculator, 0.416. Using these figures. And there we go. That's why it said hence, because it was all about the symmetry and working out that pattern there. That's quite a neat question, I thought.
Worked out like a long method.
You get
this method, you would not get the marks.
No, you'd still get the marks for that, I'm pretty sure. Okay. Thanks, John.